And hello, welcome back, OpenFOAMers, to our continuing discussion on the pimple algorithm. The last video we're talking about getting your feedback, right? So we needed some kind of feedback using the guessed new velocity field. We wanted a feedback on what the next guess of the pressure field should be so that we can iterate it, hopefully, to reach our velocity field, which satisfies both the momentum and mass conservation equations, or else known as the continuity equations. So we were stuck here in our so-called algorithm. So the next thing is to derive some sort of algorithm, which we need an algorithm which guesses a new pressure field based on the new velocity field here, which I was talking about. Right, so I need a new pressure field. Okay, so I'm going into something called pressure velocity coupling. So this is going into pressure velocity coupling. So whenever you hear this term online in the CFD community, it is basically, all right, I'm getting a new guess of pressure based on the velocity in this algorithm. So this is what pressure velocity coupling is all about. How is it being done? So we go back to our Navier-Stokes equations here. We look at our momentum equations, right? We look at our momentum equations, and let's say we want to write a neater form of these momentum equations. So how would this look like? If you go to Wikipedia, this is what the incompressible Navier-Stokes would look like. So let's start by simplifying the equations so that they look a little neater. All right. So I'm going to write that down, partial t of u, all right, plus u bullet nabla. So this is the convective term, minus nu nabla square u equals to minus nabla w plus g. So what is this w and what is this g? Basically, I have just divided throughout by density. So that over here you divide out by density so that the rho is gone. And this w here is basically just p divided by rho, which is the density. So that is w. So if I just replace it like so, p divided by rho, that is all that w is. If I divide throughout by rho, I will get just gx, gy, and gz here, which is this g vector. And of course, if I divide the dynamic viscosity by density, that will just be mu over here. Alright, so this is what we get here. Normally speaking, this g is constant. We can kind of shift it over to this side, right, so that we can kind of get this pressure per unit density. Alright, we get this pressure per unit density, p divided by rho plus minus g plus whatever else is over here. Okay, so what we have is all the pressure terms on this side and all the velocity terms and some of the body force terms, the gravitational terms on this side. So I'm not going to go through the math. Yes, if you want to go through the math, you can go through what this Fluid Mechanics 101 channel. This gentleman, he goes through this equations very nicely. So I'm going to stop short of saying that, okay, this is where our pressure feedback is, and I'm going to substitute, do some math magic, and substitute the continuity equation in. So the pressure feedback equation, so I'm going to skip out on all the math. I'm just going to go through the concept to give you an intuitive feel. So the pressure feedback equation equals momentum equation plus continuity. This is a very high level overview, and this is known as the Poisson's equation. So for more information, you can take a look online. Okay, Poisson equation for pressure. Alright, so they give more detail on what the derivations are like, but basically you will see that, alright, I am just having the momentum equation. I'm doing some math magic, which is all the substitution here, and then we apply continuity equation here. So that's what the Poisson equation is. And if you want to see how the substitution is done, you can read up on it about it, or you can watch the videos provided by this Fluid Mechanics 101 guy. Okay, so the Poisson equation provides us a pressure feedback. So we have three equations now. We have three equations now. One is the momentum equation, one is the Poisson equation, and this is the momentum plus continuity. So this will help us give the pressure feedback we need. So I'm just going to put pressure over here, and the last one, it is called just the continuity equation. And now, at least conceptually, since we have a pressure feedback kind of system, all right, we now have a pressure feedback system. We can solve it, the equations. So with these three basic overviews, and we kind of cycle through these equations over and over again to iterate them, this is the basic backbone of the simple algorithm. Simple algorithm. What is a simple algorithm? Okay. So if you take a look at the Wikipedia, okay, in CFD, the simple algorithm is a widely used numerical procedure to solve the Navier-Stokes equations. Simple is an algorithm for semi-implicit method for pressure-linked equations. So it's a very nice acronym. Yeah, but it basically does the job there and then. Okay, and normally this is you will see some of these solvers in OpenFOAM, normally used for steady state solutions, steady state situations. All right. So if you want to have a flowchart, I have this flowchart from this book called Computational Fluid Dynamics, a practical approach. So this is a pressure velocity coupling, which I was talking about earlier, a very high level, very conceptual. I didn't go into the deep maths about it, the mathematical parts, but this is pretty much more or less what the simple algorithm is like. And this is the backbone of pretty much what we can use to reference all other algorithms as well. So, okay, so this is what the flowchart is like for the simple algorithm. flowchart from computational fluid dynamics practical approach. This is from a Kindle book I got. So what does it do? Basically, it solves the momentum equations, and then we get some velocity field. We can see here that. Then we solve the pressure correction equations, otherwise the Poisson equation. Then we kind of use that new pressure to feed back into the original momentum equations. But of course, if we have other transport equations, for example, we have the turbulent transport, we have temperature transport for heat convection equations, then we do that as well. Then we have this thing called check residuals, meaning to say we check how much the solution has it moved forward, or is it converging? Is the guess of to see whether it's converging, we want to check whether the initial or the previous guess was close to the next guess. Okay, so if we have an initial guess here, and let's say the next guess is here, so the residual is kind of the difference between both of them. If the residuals are small, if the n plus 1th guess is pretty much the same as the nth guess, then the residuals are small, and then we can say the solution has more or less converged, and we have found a solution. Alright, so this is what residual checking is about. If the solution is converging, then yes, we kind of solve everything, which means the previous guess of the velocity field is pretty much the same as the present guess of the velocity field after you gone through all the checking steps, the substitution steps. If not, we take the next guess of pressure based on the pressure feedback thing, and we solve the momentum equations again. We keep doing this until there is a solution which you can solve the. We keep doing this until the solution converges, in other words. Alright, so this is basically what the simple algorithm is. Okay. So previously we went through something called a Piezo algorithm, and again we have this other guy who not this other guy, but the Fluid Mechanics 101 guy, very smart. He went through this Piezo algorithm in very much detail. So I'm just going to truncate what is being discussed there, just to give a very intuitive feel as to what's going on. So let me copy and paste here. So basically, these 4 or 5 steps are basically what comprises the simple algorithm, right? So, but for the Piezo algorithm, there is one slight modification. So why is there a need for such modification? So what's the story behind the Piezo algorithm? Yeah, for convenience sake, I actually just have our Navier-Stokes equations here. Okay. So remember we have three kinds of equations, basically. I mean, more or less 3 groups. One is the momentum equations, which are these Navier-Stokes equations, the first 3 ones that give us usually the most headache. Then we have the pressure correction equation, which is the Poisson equation which we are talking about. That's basically that step. And then we have the continuity equations. So we have the Poisson equation as well. Pressure equation. Remember, this is very important because it gives us the pressure feedback we need to find the next guess of velocity fields, right? Okay, so since we have talked about that, then yeah, the next thing is why do we need this Piezo? So the story is this. Well, every time we solve this momentum equations, you know that the computational cost is pretty high. Therefore, every time you kind of loop go through this loop of doing the momentum, the Poisson equation, and then the continuity equation. When we keep doing that, it is pretty computationally expensive. So well, how is there a way to kind of reduce that computational cost while kind of maintaining some sort of accuracy? So there was a way, especially for transient simulation, as long as the Courant number is stable enough. What you can actually skip out on this step. You can just do this step once, and instead of looping all the way around here, you can do the loop in here instead. So this kind of green circle I'm talking about is kind of called the inner loop. The inner loop. Alright, let me so the inner loop is basically just the Poisson equations and the mass conservation equations. Alright. But the outer loop will involve the momentum equations. You solve them all over again. So it's called outer loop. So this is the outer loop. Alright. So if the Courant number is small enough, we were talking about Courant number before, normally just running through the inner loop several times, that is enough. You can do the momentum equation one time, and then we run through the inner loop twice. You do the inner loop twice, 2 times of the inner loop, 1 time of the outer per iteration. Yeah, 1 time of the outer loop and 2 times of the inner loop per iteration. Yeah, if you do 1 time of the outer loop and 2 times of the inner loop, so yeah, we have a situation of 1 time of outer, 2 time of inner per iteration. Now, if the Courant number is small enough, so it's like less than 1. Okay, less than 1. If the Courant number is small enough, you probably only need 1 outer and maybe 2, 3, 4 inner loops. So 1 outer loop per time step, then followed by 2 or 3 inner loops per time step for it to converge properly. So that's when the Courant number is smaller than 1. You can kind of skip the outer loop, what do you call that? The outer loop per iteration. Alright. If it gets larger than 1, then probably you need to calculate the outer loop a little more per time step. Okay, but this is the Piezo algorithm. So simple algorithm is like this, okay? And why did I say that this can actually save what do you call it, computation time? So this is a simple algorithm. Let's say the simple algorithm takes 50 iterations. Right? 50 iterations. Alright. Okay. So let's say the simple algorithm takes 50 iterations, and that is basically 50 times of the outer loop. Okay, let me use typing to make it faster. 50 times outer and 50 times inner, or 50 times outer, right? 50 times outer means the 50 times of momentum. Alright. plus 50 times Poisson plus mass continuity. Now I did say before, this Poisson plus continuity tends to be less computationally intensive than the momentum equations, right? Now you might wonder, hey, if this Poisson equation is derived from this momentum equation, will it not become like more computationally intensive? Well, you just have to take my word for it that the mathematics, the math magic you kind of do behind it, it will make it less computationally intensive. Now, the details, of course, are found in the other video by the Fluid Mechanics 101. In the Fluid Mechanics 101 video, you can do a little more study into that. And let's talk about the piezo instead. Yeah, the piezo. And remember, this is for steady state, yeah? Steady state. Now, normally simple is being used for steady state, but of course you can use it for transient simulation as well. Nothing stopping you from that. But let's have a piezo for comparison. Let's have a piezo for comparison. And that maybe instead of 50, you have one iteration. Okay, one iteration. Okay. So one iteration, and what would that iteration look like? Okay, so you have one outer plus 50 inner. So this is just an example, I'm just making up numbers. So solve the momentum equation one time, and 50 times Poisson plus continuity. Okay. And why can you exploit this? Because a small Coulomb number, right? A small Coulomb number gives me the chance to exploit. Okay, I can skip out the momentum. Small Coulomb number gives me the chance to exploit the fact that I can skip out on that momentum equation calculation. I can just do it once. Now I just cycle through the Poisson and continuity equation maybe 2-3 times or maybe 50 times if needed. But what the reason why we can do this is we have a small Coulomb number. Now normally, of course, we may not need we may not actually need like 50 iterations just for one time step. All right. We may not need 50 iterations for one time step. Maybe 5 to 10 or 30. It depends on the simulation. Yeah, but the small Coulomb number will enable this, and therefore it kind of saves us. It saves us, let's say, one time step instead of 50 times of this momentum and Poisson equation. You can have 1 and 50. So this kind of saves us computational space. Of course, maybe you can have a situation where the simple algorithm needs to be solved 20 times, right? Because when you solve the momentum equation, you include that in, maybe it takes less iterations to converge per time step. Alright. However, if you're solving the momentum equation 20 times, and you solve the Poisson equation 20 times, the momentum and the Poisson plus continuity. Yeah, this may still be more. This may still be more computationally expensive than this. Of course, if you have less iterations, maybe 10 or 5, maybe this thing starts looking more computationally expensive. So there's no hard and fast rule to this. But when there's a small Coulomb number, you can exploit the fact. You can exploit solving the momentum equation once, and then the Poisson and continuity equation you solve many times. So that's what the Piezo algorithm is based upon. If you have a small Coulomb number, then we don't need to solve the momentum equation so many times per time step. So it's a per time step basis. So that's why Piezo was kind of invented. See, Piezo was invented so that, you know, per time step you take less computational power. Of course, if you have many time steps, right? If you have many time steps, or if your time step is so small that you need a lot of frames that you're calculating, then of course the cost benefit you kind of have to weigh yourself. So yeah, okay, but this is why Piezo. This is the main difference between Piezo and the simple. How many times is the outer loop being calculated? Meaning how many times is this momentum equation being solved per time step, as compared to the inner loop, which is the Poisson and continuity equation. So this basically outlines the key differences between the simple and Piezo algorithm. So I'll stop here for now, and I'll see you in the next video.